You ever look at your heating bill, especially in the middle of winter, and just wonder where all that money, all that energy is actually going? Well, the answer is all around us. It's just written in the language of physics, and today we're going to learn how to read it. So take a look at this. This is a thermal image of a house. See all those bright red and yellow spots? That's heat, literally pouring out of the building. This is where your money is escaping into the cold air. It feels like it just disappears, right? But here's the thing, it doesn't. And if we can understand where it's going, we can start to control it. To do that, though, we got to talk about the basic rules of energy. To answer that question, we need to get into the rulebook for energy itself. And that rulebook is called thermodynamics. Now I know, it sounds super complicated, but at its heart, it's just the science of how energy moves and changes. It governs everything from your coffee maker to the entire cosmos. Okay, so the very first rule in tracking energy is deciding what exactly we're tracking. Before we can even start to do the accounting, we have to draw a line around the thing we want to study. We need to define our boundaries. In physics, this is called a thermodynamic system. It's really just a fancy way of saying the thing we're looking at. It could be your living room, your whole house, or even just the water inside your pipes. We draw a little conceptual box around it so we can see what goes in and what comes out. And that brings us to the two main types of systems. So on the left, you've got the house. You can see energy, sunlight coming in, heat leaking out. It's crossing the walls. But the house itself, the actual stuff inside, mostly stays put. That makes it a closed system. Now, look at the boiler on the right. Water and gas are constantly flowing through it. The actual matter is crossing the boundary. That's what we call an open system. And that's really the key difference right there. With a closed system, you're tracking a fixed amount of stuff, like the air trapped inside a house. But with an open system, you're watching a fixed space, like the inside of that boiler, and you're just tracking what flows through it. Knowing which one you're dealing with is step one to balancing the energy budget. All right, so we've drawn a box around our system. Now, how do we describe what's happening inside that box? How do we take a snapshot of its condition at any given moment? Well, to do that, physicists talk about something called the system's state. And a system's state isn't as complicated as it sounds. It's really just a list of its vital statistics, things we can measure, which we call properties. You already know the most common ones, temperature and pressure. It's kind of like describing a person by their height and weight. And these properties come in two main flavors. You've got intensive properties, like temperature or density, that don't change no matter how much stuff you have. A single drop of water and an entire ocean can both be the same temperature, right? But then you have extensive properties, like mass and volume, which, totally depend on how much you've got. Now, in a perfect, simplified world, a system could reach this ideal state called thermal equilibrium. All that means is that every single spot inside our system, inside our house, is at the exact same temperature. Nothing's hotter, nothing's colder. And in that state, heat doesn't really flow because it has nowhere colder to go. But you and I both know reality is way messier than that. As our source material points out, a real building is never perfectly uniform. The ceiling's going to be warmer than the floor. It's going to be colder by the windows. And you know what? That's okay. These simple models are still incredibly powerful for helping us figure out what's going on in the real world. So, we have our system, and we know how to describe its state. Now we get to the good stuff, the energy itself. In thermodynamics, it really helps to think about energy as different kinds of currencies that can be exchanged and accounted for. And there are three main players on the field. First, there's internal energy. That's all the hidden, microscopic energy of the molecules just jiggling around inside the system. Then there's heat, which is specifically energy that's on the move because of a temperature difference. And finally, there's work, which is energy transferred when a force actually moves something, like a piston pushing up. This simple diagram shows it all perfectly. If you add heat to the gas in that cylinder, only two things can happen to that energy. It can be absorbed by the gas molecules, making them zip around faster. That's an increase in internal energy. Or the energy can be used to push that piston up and do some work. It's got to be one or the other, or some mix of the two. And believe it or not, that simple little piston example contains the single most important rule in all of thermodynamics, the first law. And the best way to think about it is as a perfect, unbreakable energy budget. It's got a big, important name, but it's actually a concept you probably already know. The conservation of energy. The first law just puts a formal name on it. And this is the entire law in one simple idea. Any heat you add to a system has to be accounted for. It either does work or it raises the internal temperature. Every single joule of energy has to go somewhere. Nothing is ever lost. And this is the big takeaway. Energy is like money in a bank account that has perfect accounting. You can't just create it out of thin air, and you can't destroy it. All you can do is move it around from one account to another, from heat to work, from sunlight to internal energy, but the grand total, that always stays the same. And this brings us right back home, literally to our house. We can actually see the first law playing out. All the energy coming in from the sun, your furnace, even your laptop, that has to equal all the energy going out through the walls, the windows, the roof, plus any change in the heat that's actually stored inside the house. The budget has to balance. So think about what this really means. The first law tells us that saving energy is kind of the wrong way to look at it. The energy is never actually destroyed. The real game is getting better at managing it, at controlling its flow, at keeping the heat energy where we want it for as long as possible. Which brings this all back to you. Now that you understand the budget, you can look at your own home in a new way. The first law is at work in your living room right now. The only question left is, where's the biggest leak in your budget?